welcome back. This is part 2 of this week's lecture. This part we're going to introduce the induction motor and its working principles, particularly three-phase induction motors, because they are the most used motors for industry. It has a simple construction, low cost, low maintenance, and can generate high torque. AC induction motor is invented by Nikola Tesla 100 years ago. Actually, 50% of the global electricity consumption is used for AC induction motor, and 90% of industry motor is AC induction motor. You can see the figure of the motor. There's a cooling fan on the left end, and the shaft on the right, so going in the center, and the shaft is connected to the rotor in the middle, and outside is a stator. So if you have a AC current going through the stator, then the induction current will be generated inside the rotor, and also the rotor will move inside and turning the shaft. This is how they generate the movement. This figure is a explode view of the three-phase AC induction motor. It has many other components like the cooling fan cover. There's a bearing on each side, and in the middle is the stator, and what we have outside the stator, there's a case. Inside there's the square cage rotor and some bearings, and there's a shaft also attached to it. There are two most important components in an AC induction motor: the stator and the rotor. The stator will have a AC current going through, so it's a kind of coil, and generate a magnetic field. Because it's AC current, the magnetic field will changing with the AC current change. Inside this stator will be a rotor. The rotor is also called a squirrel cage because the shape is very similar to a squirrel cage with aluminum bars that connect the current from the both ends. This rotor has no external current applied. Because of this kind of structure, the stator current will excite the rotor to generate excited current, and also excited current will generate the movement for the rotor. The rotor is connected to the shaft, which will provide the motions and connect to the outside. The rotor look like a cage. We normally call it a squirrel cage. These golden colored bars are typically made of aluminum, and these bars are a little bit kind of tilted to generate the power kind of more continuous. The end rings also made of aluminum, and the end rings and these bars will generate kind of closed-looped circuits, which will have the current flow if the magnetic field outside is changing. The iron laminates are put in between the end rings. In the actual case, it will be kind of filled all the gaps to kind of provide larger magnetic field. In here, there's only 3 of them showing, so make these aluminum bars like more visible. How does it work? To generate voltage, we need to have a magnetic field, a conductor, and a relative motion between them. This is how a generator works. Actually, a motor uses the same effect, but in a reverse order. So essentially, to generate motions from electrical motor, we need 3 things. Firstly is a magnetic field. It can be a permanent magnet or electrical magnetic generate magnet. Secondly is a conductor. A conductor must inside the magnetic field. And 3 is the current needs to going through the conductor. And with these 3 conditions, then the conductor inside the magnetic field will under the force from the magnetic field and will have relative motions. Like this, the electrical magnetic force will be generated on the conductor if this conductor has current going through it and it's under a magnetic field. We have a three-phase AC waveform coming from the power supply. Each one of this waveform is a sine wave, and they are 120 degrees in phase difference. So we have a magnetic field which is moving, changing its magnitude and changing its direction. We have a rotating magnetic field in the stator. At the stator, because the current changes, the magnetic field also changing, rotating around. In the rotor bar, the excited current will generate another magnetic field, and this magnetic field trying to align with the rotating magnetic field from the stator. It's trying to catch up, but never actually catch up, because if it's catch up, then there's no current inside the internal. So it's always kind of trying to catch up a little bit behind, which we call it slip. This YouTube video actually provides a very good explanation for the principle of AC motor.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts: stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So induced current and force will rise again, and the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor.
Hope you got a good introduction on the working of induction motors. Thank you. Induction motors are the most commonly used electrical.
The speed of rotating magnetic field is also called a synchronized speed, and it can be calculated by Ns equal to 120 F over P. Here Ns is a synchronized speed in RPM. F is the power supply frequency. In Australia, that's 50 Hz. In USA, 60 Hz. So most part of the world is using 50 Hz. Some part is using 60 Hz. There's nothing else. Divided by P. P is number of poles. The winding of this stator can make the north pole and south pole in groups. You can have only one north pole and one south pole, so you have two poles, or you can have 4 poles and also 6 poles and 8 poles. Depending on how these stator wires are connected, you can have a different number of poles. You can have 2 poles, 1 north, 1 south, 4 poles, which we have 2 north, 2 south, interconnect to each other, and you can have up to 8 poles. That's all kind of commercially available. Compare with more poles and less poles. From the last page, the formula, we already know that if we have more poles, we'll have a slower speed, because the speed has the poles at the denominator. And because it's slower speed, with the same size, it actually will have a larger torque. And also, if you have more poles, means the winding is also going to be more complex, and the motor is going to be more expensive. And if it's slow enough, you might not even need a gearbox in some case. So most commercially used ones are 2 poles or 4 poles, but you can find 6 poles or 8 poles motors as well. But what about slip? The slip is some special feature for AC induction motor. When we talk about DC motor, there's nothing kind of relevant terminology over there. If the rotor runs at a synchronized speed, the same speed of the rotating magnetic field, then there's no relative motion between the stator field and the rotor conductor. Then the rotor will have no induced current. There's no current inside the rotor, then there's no torque coming on the rotor. Then the rotor will slow down. So the balance point is where the speed of the rotor is slightly slower than the stator magnetic field. And this difference is called slip. If we increase the load, then the rotor will slow down a little bit, will increase the slip, and which will generate more heat. If we decrease the load, then the slip will be reduced, and there will be less heat. So normally the slip is about 4% for this induction motor. From the formula, Ns equal to 120 F over P. F is 50 Hertz in Australia, and pole can be 2, number of poles, 4, 6, 8. And we can then come up with this normalized nominal speed in the catalog. So the synchronized speed can be 3000, that's 2 pole, up then goes to like 600, that's 10 poles. And the slip is normally 4%. That's when the motor is fully loaded at the nominal loading point. The slip is 4%, so we got our actual output speed of the motor is 4% less than the standard. So 1000 actually got 960 RPM. So for a motor, we can't really choose any speed at the motor. The motor speed is pretty much given in these kind of ranking numbers. This means based on the gear ratio, you can't really get exact motor speed. You should get a motor speed that's very close, then go back, recalculate the gear ratio again based on this nominal rated speed of the motor output. When we design a 3D induction motor for a certain application, not only we should consider when it's working at a steady state, the torque, the power, and the speed of the motor needs to suit the application. Also, we should consider the startup process, because the motor needs to go from the steady state up to the rated speed. So motor needs to speed up. There are two things you need to consider when they speed up. Firstly, the torque needs to be always larger than the required torque. The motor torque always needs to be larger than the required torque. Secondly, is the starting process should not take too long. If it takes too long, then because of the current through the motor when they start up is going to be very large, then the motor is going to overheat it. So first, let's look at the torque. For our conveyor, the torque of the load is a constant. We can consider it roughly as a constant. So the requirement is our torque from the motor needs to be always larger than this payload torque. Otherwise, when it goes through a certain point, then the payload is larger than the motor torque, then the motor cannot speed up and reach our rated speed. So for the motor torque, the green line shows the motor torque curve. There are a few important points on this line. The starting torque, pull-up torque, breakdown torque. This is the largest torque the motor can supply. And then this full load torque. So normally the full load torque is giving you any torque values, and the other three give you a percentage based on this full load torque. So for example, in this particular motor design, starting torque is 100%, 150% of the rated full load torque. Pull-up torque is 125%, so it goes a little bit lower. Then the breakdown torque is 200% of the full load torque. So you can see the torque curve. The smallest value is when it's pull-up torque. So that's kind of the dangerous point. If our payload is larger than that, then it'll never going to be start up to the full speed. The second thing is we look at the current curve. So you can see the current goes from 600% of the standard load current, and then you drop down. So when the motor is the static, the current is the largest. Then the current drops down when the motor speed up. So this period of speeding up needs to be short enough so the total motor heat generate, the heat is equal to I square multiplied with R. R is resistance of the coil. So that needs to be fast enough. So the energy generate, the heat generate during this speed up is not too much, so the motor will not be kind of too hot and getting damaged. Let's look at a small portion of the curve to look at when the payload increase, what's going to happen for the system. Say the system at the beginning is working at this red point. So it's at the rated speed and with a rated torque. The payload is at the rated value. And when the system has payload increase, so you can see it moves from this red point to the blue point. So the torque increase because the payload, say there's extra material putting on the conveyor, it becomes heavier, you need more torque to move it. The speed of the system will go down because it moves along the green curve, so it goes left up, and you see the current of the system actually will increase. So when the load increase, the motor speed will decrease, and the system will draw more current and then generate more heat. So that's why we normally want our payload to be at what's designed payload. If we get extra payload more than that, then the system might get overheat. And this point can keep going until it reaches that green spot, which is a breakdown torque. If the payload actually reaches that point or past that point, then what will happen is the torque of the motor is not sustainable to provide this overload. The motor will continue to slow down until it will stall, and the system will generate a lot of heat. Then the motor will actually being damaged. How do we start a three-phase induction motor? We can simply say we just do a hard start, or we call it directly online start. So we just connect whatever the normal operational AC power directly to the motor. So the motor will follow this red line. The current will be very high at the beginning, then hopefully we design the motor has enough torque so it can speed up quickly enough so the heat is not going to damage the motor. Motor can operate in a normal condition after a few seconds of speed up. Advantage is actually it's very simple. You don't have to get extra circuits or relays to connect your system, and it's very robust because it's simple. But the problem is there's a large current at the startup period. If your payload is actually high, then the startup period may take too much time, and this long time with high current will generate a lot of heat. So if you follow this red line, your system will follow the red line. So that's kind of simplest way to start. Basically, we don't do anything. We just connect the motor directly to the power and just turn it on. But there must be something better way, particularly when you have a heavy payload and your motor will take a long time to start. With this direct hard start, there might be some problem causing to the system. If we just connect the motor directly to the supply voltage, at the beginning there will be high voltage and also high current, which are causing that hard start problem potentially. So a softer start is quite straightforward, that we reduce the current. So how do we reduce the current? We reduce the voltage supplied to the motor at the beginning. This will take the start time even longer than normal, but because the current is reduced and the heat is equal to I squared over R, so even the time might be a little bit longer, but the overall heat generated will be smaller, and then it won't kind of overheat the motor or will cause less disruption to the other supply on the system. There are a few ways to achieve soft start. The most popular way is we call star data connection. So in the figure, there's SSW06 soft starter. So basically, this device can switch the wire connection between a delta connection and also a star connection. This is the two different ways how the three-phase AC current be connected. You connect this box to the motor from one end, and the other end connect to the power supply. If you're from SECTI, you definitely learn this from power electronics. The 3D phase electricity can be connected through either delta or star connections. So when you connect in a star connection, the voltage is only 1 over square root of 3 of the delta connection. So through this kind of connection, we can reduce the power supply voltage at the beginning of the startup period by 1 over square root of 3 of the normal voltage. And by doing that, then the current is also 1 over square root of 3 smaller than the normal current. Then the heat generated during the startup will be smaller. Things to remember is when we do soft start, because we reduce the supplied voltage, the torque from the motor is also reduced. Remember, we have a pull-up torque, which is kind of the lower point during the startup. When we do this soft start, we have to make sure that lowest torque, pull-up torque, needs to be bigger than the payload torque. So that's a guarantee that the motor actually can start. Otherwise, if we have that torque is less than the payload torque, then the motor will never be able to start. So again, there must be some better way of addressing this. The better way is called a variable frequency drives. It's short for VFD, and also another name is called a variable speed drive, VSD. So this device is much more complicated than the soft starter we mentioned in the last slide. You can see there's many more terminals for this device, and they connected between the power supply and the motor. It actually can achieve changing the voltage and also the frequency of the voltage to the motor with many different combinations. And also the torque and running direction can also be changed. So this virtually provides unlimited kind of possibility for the motor to run. And during the startup, you can program to in a certain different frequency and different power supply to change the feature of the motor supply. But obviously, this is a much more complicated device compared to the starter. Then it will be more expensive, but it's still getting more and more used to replace that soft starter or just connect the motor directly on the line. Back to a basic question, how do we actually control the motor speed for an AC induction motor? The synchronized speed of the motor, Ns, equal to 120 F over P. Here, Ns is synchronized speed, F is the power supply frequency, N is number of poles. So once we have a motor, the number of poles is determined. The only way to change the synchronized speed of an AC motor is by changing the power supply frequency. For the direct online connection, you connect the motor directly online, you can't change that frequency. In Australia, it will be 50 Hertz. So the only way to change the speed is actually connect that to a variable speed control or frequency control drive, and use the drive to adjust the supply frequency to the motor. That's it for this part. Here are a few questions that you need to think about. I'm going to go through these questions during the lecture time. Look at these questions and think about, do you have an answer for these questions? If you don't, please go back to the slides and videos and try to figure out an answer for that. At the end, I'll provide 2 more videos to you. Actually, many of YouTube videos, they are in very high quality with beautiful animations, which is